Hello, welcome to our first video lecture for Chapter 2. So this is video lecture 2.1, where we begin our study of motion along a straight line. So let me go to my first slide. Chapter 2, motion along a straight line. Let me start by pointing out that there is content that you can read from our textbook. Our textbook is a digital textbook on a website known as Wiley Plus, because the publisher's name is Wiley. The title of the textbook itself is Fundamentals of Physics, 11th edition. In these video lectures, I summarize the material that you can read from the book. But I strongly urge you to read the material from the book because there's a lot more detail and a lot of example problems there. So let me show you what that material looks like on the Wiley Plus site. Now, I've already sent you a separate document with information about how to obtain access to the Wiley Plus site. That is where you are buying access to our textbook. And when you purchase that access to our textbook and log in to the Wiley Plus site, to read our textbook, this is the home page that you will see. Okay? It says Wiley Plus. The first name of the first author that you will see, that person's last name is Halliday. The title of the book is Fundamentals of Physics. It is the 11th edition of the book. This is the home page that you will see. And you see a menu along the top. And you see one of the buttons is Read, Study, and Practice. So if you click on that, you will get a screen that lists, I'll click on this button first, another menu with a drop-down list of all the chapters in the book, and you want to choose or select Chapter 2, Motion Along a Straight Line. And then you will see chapter resources, reading content, and section 2.1 is hyperlinked, position, displacement, and average velocity. And if you click on that, wait just a moment, you will get the actual reading content from chapter 2, section 1, position, displacement, and average velocity. And then you read. You just start reading. And I strongly encourage you to read this content. Read every word of it. You'll love it. It is clearly written, very accessible, and one of the things that makes our textbook unique amongst all the physics textbooks on the market is that it has embedded a little assessment questions. You can try them. They don't count for anything point-wise, grade-wise. They're just for you to practice. Okay? And they're meant to help you assess if you're understanding the reading as you go along. So it poses a little question. You enter an answer, you scroll down and there's a button, check answer, and you can click on that to see if your answer is right. And if you don't want to do all that, you can just click on this button that says Show Solution. And when you click on that, a little mini window will appear when you're reading it online. It doesn't show up in this video, but it will when you're reading online, and it will show you the solution to that question. And you can go through all the reading. There are a number of embedded questions. Okay. There are a list of learning objectives and a summary of key ideas that you just read, and then more applications by means of example problems with embedded questions as you go. Okay. So when I refer to reading in the text at the beginning of a video lecture, this is what I'm referring to. I strongly encourage you, if your time permits, to read this content because my video lectures are merely summarizing what is in the reading. And now I'm going back to my summary of the reading, and I am summarizing Chapter 2, Section 1, position, displacement, and average velocity. Okay, so let's begin. With this chapter, we begin a 3-chapter sequence on what is called kinematics. In kinematics, we are describing the motion of an object without addressing without addressing what's causing that motion. We'll save the study of the cause of a motion for later on. Now we're just going to describe how a particle is moving with descriptive words. But more than just words, also mathematics. Quantitative description is what we mean. This is science, after all. And science is precise and specific. And in physics, when we describe motion, we use math. Lots of math. So when I say describing the motion, I mean something more than, oh, look, there's an object and it's moving around. Isn't that pretty? Okay? So you'll see as we start bringing in all kinds of very specific terms how we're going to describe the motion of an object. We're also going to limit ourselves to the motion of what we call particles. And by particle in physics and in kinematics specifically, we mean any object in which every part of that object moves in exactly the same way at any given instant. One of the things you'll come across if you do the reading in Wiley Plus for section 2.1 is a little animation that your author shows showing the motion of an armadillo moving along an x-axis. And the armadillo's motion is rigid. Every part of it is moving in exactly the same way along an x-axis. That's the kind of motion along a straight line of a particle that we're going to focus on in Chapter 2. If you want some other examples of things that are more realistic or more everyday, you don't often see an armadillo moving around, that we would put into this category, say a drag car, a drag race where cars move in a straight line, or an airplane on a runway during its takeoff roll, but before it starts to take off and leave the ground and it's moving along the runway, you can think of that as motion along a straight line. And we'll see other examples. That's the kind of motion we're going to focus on in Chapter 2. So to describe that motion, what do we do? Well, we're going to define some very specific terms or quantities that we will use to help us describe the motion of a particle. So let's start looking at the various quantities that we're going to define. First quantity, position. Position is just a location or a coordinate on a chosen axis relative to a chosen origin. So here you see a depiction of part of an x-axis with a chosen origin, and we can have some particle, maybe it's an armadillo, maybe it's an airplane on a runway, maybe it's a drag car on a raceway, whatever it might be. And it's going to be moving along on this x-axis. And at any given time, any given instant, it has a position. It is located somewhere on this axis that you see. And you'll notice that this x-axis has a scale of meters. You can see the m over there on the right by the x. That tells you that the numbers that you see on this x-axis, like the 1 or the 2 or the 3 or the -1 or the -2 or the -3, is an x position in meters. And then the symbols we use are x if the object's moving along an x-axis, or y if it's moving along a y-axis, or z if it's moving along a z-axis. In Chapter 2, we tend to use x for a horizontal axis, an axis that's along the ground or parallel to the ground. A vertical axis, we tend to use y. That's just kind of convention. But position is a coordinate that tells you where the particle is located at any given time. Now, if the object is just sitting on the x-axis and never moving, then its position is never changing. That's going to be pretty boring. We're not going to limit ourselves to just that. We're going to be more interested in particles that change their position on an axis, such as an x-axis. Right? They're moving around. So we need something more than just position, or at least it's useful to have something more than just position. The next quantity we're going to define is called displacement. And by definition, displacement is change in position. Note the emphasis on the word change. Now the SI unit of displacement is still meter, symbol for that unit m, but now the symbol for the displacement, let's say the particle is moving along an x-axis, is delta x. That's a Greek capital letter delta followed by an x, meaning change in position. Okay? Final position minus initial position for a given time interval that has to be specified. And displacement is where we start to emphasize what we call vector quantities. And any vector quantity has both a magnitude and a direction associated with it. The magnitude of a vector quantity can never be negative. It's just the absolute value, if you like. And the direction, which is denoted by a sign, is, at least for our horizontal x-axis that you see up above, either the positive direction of x, to the right, or the negative direction, to the left. And so if a displacement delta x is a positive quantity for a given time interval, what that's telling you is that the particle ended up to the right of where it started. If the displacement delta x for a particle is a negative quantity, that's telling you that the particle ended up to the left of where it started. So displacement allows us to keep track of how much the position has changed in a given time interval. Now let's go to our next quantity that we find useful to define when we're studying or describing the motion of a particle. And that next quantity is defined to be average velocity. Now we're starting to expand our horizons a bit. Not only do we want to keep track of how much a position has changed, but how rapidly has that position changed? That is often a useful thing when you're describing the motion of a particle. And so average velocity is the rate of change of position over a finite time interval. Or to say it another way, it's the displacement in a given time interval divided by that time interval. What is the SI unit of average velocity? Well, it's the unit of displacement divided by the unit of time interval, so meter per second. What are the symbols that we use in this book for average velocity? I'm going to focus for motion along an x-axis. The symbol is v with a subscript avg, average velocity. It is defined to be, three lines here mean this is the definition, displacement over time interval, delta x divided by delta t. And then you see another way to express that, at least used in this chapter, x2 minus x1 over t2 minus t1. So we're talking about a finite time interval that begins at the time called t1, where the particle had position x1, and ends at the time called t2, when the particle had position x2. And with those definitions, the average velocity is computed by taking x2 minus x1 in the numerator and t2 minus t1 in the denominator. Average velocity, like displacement, is a vector quantity with a magnitude and a direction. And its direction is the same as the direction of the displacement of the particle for the given time interval, because displacement is right there in the numerator in the definition of average velocity. Okay, so what I want to turn to now is a little animation to have us visualize the motion of a particle and get some practice with these ideas of position, displacement, and average velocity. So now I'm going to transition back to Wiley+. And I'm going to click on a different tab here in my browser to a simulation or animation that I have already opened. It is on Wiley+. You can find it on Wiley+. Horizontal motion of a bead on a smooth wire. And it's going to represent a bead moving along an x-axis, where the x-axis is a smooth wire, and the bead has been threaded onto this wire and can move on this smooth wire. And something, we don't care what right now, is causing it to move. And we're going to run an animation. It's going to start at time 0, t equals 0, and it's going to end at the time chosen by this slider labeled t stop, which right now is 1 second. So when I run the animation, it's going to run for 1 second. It shows the bead as a red disk on the x-axis. You can see that it's currently located. Its current position is x equals 2 meters. Let's run the animation for this 1 second time interval and see what we observe. Okay, in this time interval delta t, between t equals 0 and t equals 1 second, the x position changed from x equals 2 meters to x equals 4 meters. So, what was its displacement, delta x? Pause the video and answer that for yourself. Okay, did you pause it? Did you think about the answer to my question? What is the displacement of this particle, this bead, on this 1 second time interval? What is delta x? And did you say that delta x is positive 2 meters? Because you take x final minus x initial, x at the end of the time interval, minus x at the beginning. X at the end is 4 meters. X at the beginning was 2 meters. 4 minus 2 is 2. So delta x is 2 meters, positive 2 meters, for this time interval. There's even a little blue arrow pointing to the right here to show you that the displacement was to the right or in the positive x direction for this time interval. Now let me reset, and with this little drop-down menu, I can change when t-stop is. I'm going to change it now to 3 seconds. So now the time interval is going to start at t equals 0 and end at t equals 3. Let's observe the motion. Okay, so that was a 3-second interval. Here's a question for you again. What is the displacement of the particle for that interval? Again, pause the video, think about it for a moment, get an answer, and then come back. Okay, welcome back. Did you say that the displacement delta x for the time interval I just showed you is 0? Delta x equals 0 for this time interval because x initial was 2 meters and x final was 2 meters. And even though you saw it move, its displacement for this time interval is 0. So here comes another question for you to ponder. Is displacement, symbol delta x, as we've defined it here, the same thing conceptually as the distance a particle travels? Think about that. Pause the video, think about it, and come back. Okay, welcome back. So, generally speaking, is displacement for a particle and distance traveled, are they the same concept? Answer, no, not necessarily. Distance traveled is just the ground covered in a time interval. So if I can slide this slider back and run it again, I can see that it travels to the right a distance a little more than 2 meters because it goes from x equals 2 to x equals 4. And then it travels back that same distance to get back where it started. So the distance traveled is a little more than 4 meters, but the displacement is 0. Okay? So you got to be careful and always think of the definitions of things. If we ask you for displacement, don't give us distance traveled. Because in physics, these words that we're defining to describe motion in kinematics have very specific definitions and meanings, and we have to adhere to those. All right, let me reset the animation. Now let me change the stopping time to t equals 5 seconds. Okay? I'm going to run the animation. Let's watch again. Okay, now there quite a bit happened in this 5-second time interval. Okay, here's the first question for you. What is the displacement delta x for that interval? Pause, answer, and come back. Okay, welcome back. Did you say the displacement for this time interval, delta x, is negative 10 meters? The negative sign is important. The particle ends up to the left of where it started, and the value is negative 10. because x final here you can see is negative 8 meters, and x initial was 2, and delta x is computed by taking x final minus x initial. Using algebra correctly, negative 8 minus 2 equals negative 10 meters. By the way, you also have to include the unit, m, for meter. Otherwise, the answer is incomplete. So the displacement here is negative 10 meters. All right, you ready for another little challenge? Calculate the average velocity for this time interval. Again, pause, think about it, and then come back. Okay, did you get that the average velocity for this time interval, v, avg, is equal to negative 2 meter per second? Why is that the answer? The definition of v average is displacement over time interval, delta x over delta t. So that's how we must compute it. The delta x for this time interval, the displacement we just said, is negative 10 meters. What's the delta t for this time interval? Well, t final is 5 seconds, t initial is 0 seconds, so delta t is 5 seconds. So we have negative 10 meters divided by 5 seconds is negative 2 meters per second. Okay, so now we have introduced position on an axis, displacement as change in position along that axis, and average velocity as displacement over time interval. And we've done some practice with that. Now I'm going to transition to a new slide. Let me get back here so you can see it. And now I am in Chapter 2, Section 2. So you can do the reading in our book on Wiley Plus, Chapter 2, Section 2, which is entitled Instantaneous Velocity and Speed. Okay? All right. Let me get this mode so that you can see it a little bit better. Instantaneous velocity and speed. So here's our motivation for defining yet another quantity to study kinematics. Average velocity is a kind of rate of change of position, but it's over a finite time interval, like the 5-second interval we just saw for the bead on the wire. There might be times when we're interested in rate of change of position, how fast and in what direction as a particle moves, but at a particular instant in time. Not over a drawn-out time interval, but at an instant. So let's introduce a new quantity, instantaneous velocity, which, by the way, most physicists just call velocity for short. Okay? But for now, I'm going to use the full terminology, instantaneous velocity. What is its definition? First, in words. In words, instantaneous velocity is defined to be average velocity in the limit as the time interval delta t approaches 0. But we mean that word limit in a very precise mathematical way, as you will be learning in your calculus class, and I'll get to in a moment. But instantaneous velocity is average velocity in the limit as the time interval delta t approaches 0. First, the SI unit of instantaneous velocity. Well, it's meter per second, because it's the unit of average velocity, which is meter per second. Now, what's the symbol or the notation that we use for average velocity? Just plain old lowercase v, script or italic v, okay, when you represent a mathematical symbol in physics. Here's its definition. 3 bars means defined. It's what a mathematician calls a limit as the time interval delta t goes to 0 of average velocity. And there's the mathematical expression delta x over delta t for average velocity. Now let me just elaborate. This is just elaborating that. It's the limit as delta t goes to 0. And in the numerator, I've now expressed what I mean by delta x, displacement. I mean change in position. The initial position is x at time, which is the position at time t. And the final position, x, is at the later time t plus delta t. And that's what this notation means in the numerator. And you divide by delta t. and you take the limit as delta t goes to 0. Now, if you're astute with your algebra, you should be a little bit concerned by this definition, because it looks like, doesn't it, that our prescription is to take this fraction, x at time t plus delta t minus x at time t, divided by the quantity delta t, and take the limit as delta t goes to 0. But the delta t is in the denominator. So it looks like I'm taking a fraction and I'm making the denominator go to 0. And my math teachers taught me that a fraction with a 0 in the denominator is undefined. So haven't we just set ourselves up for a problem here? Sure does seem so. But here's where the whole idea of this limiting process is very clever. It turns out that the numerator, x at t plus delta t minus x at t, is also going to 0. So what I actually have is a fraction with a 0 divided by a 0. And if that limit is done in a very careful way, the output, the answer, what comes out of that limit, can be finite and have meaning. And it does. And that's what your calculus professor will be spending a very long time in Math 110 teaching you about. How to do that limit and how it can be done properly, such as that you end up with an answer at the end that makes sense. Now you need to get used to the notation here, because that whole limiting process of delta x over delta t as delta t goes to 0, that's very tedious to write all that out. So we use shorthand notation, and there it is, dx over dt. That's the notation you'll see. So that is another way to express instantaneous velocity. Now to use the words, we say instantaneous velocity is the derivative of the position with respect to time. That's what this notation dx over dt means. The derivative of the quantity labeled x is the position on the x-axis, with respect to the quantity labeled t, time. Dx over dt means the derivative of position with respect to time. But we also use the words rate of change of position. A derivative measures the rate of change of a function. Okay? And instantaneous velocity is the rate of change of position. So with instantaneous velocity in kinematics, we are watching a particle and we are measuring the rate of change of its position at any given time. Now, I understand that the whole concept of a derivative is from calculus, and that may be new to you. You may have had calculus in high school. You may have only gotten up to pre-calculus. If you've not seen the whole concept of a derivative before, it can be a little bit daunting. And in a later video lecture, I'm going to be emphasizing those things that you need to understand right now about a derivative in order for us to continue in Chapter 2. Okay? So I'll have more to say about derivatives in an upcoming video lecture, but in Math 110, you're going to be spending weeks learning about derivatives. Okay, for now, let's continue. First, let's next emphasize that instantaneous velocity, like average velocity, is a vector quantity with both a magnitude and a direction. And here comes another bit of terminology that you just have to be aware of. When we talk about the magnitude of instantaneous velocity, just the magnitude part, we have a separate word for that. Instantaneous speed, and we got to use all these words correctly. Instantaneous velocity is the rate of change of position. It's a vector. When you talk about only the magnitude part, we call it the instantaneous speed, and it's just a measure of how fast a particle is moving without worrying about what direction it's moving in. And if you want to be really careful, a good way to denote the magnitude of instantaneous velocity, i.e. instantaneous speed, is to write the v symbol with absolute value over it. That way you're telling your reader, I just mean the magnitude part, the instantaneous speed, how fast. But I'm not telling you direction. The direction, of course, is the direction in which the particle is moving at a given instant. And that could be to the right on an x-axis, i.e. plus x direction, or it could be to the left, negative x. We're going to be doing practicing with these ideas, don't worry. Let's start with a little bit of graphical interpretation of instantaneous velocity. So let me go back to Wiley Plus, and now let me open up another animation that you can find on the Wiley Plus site, average velocity in the limit of decreasing time interval. And this shows a lot of information, in fact. And it's our first example of what's called a position time plot. It's a bit of an abstraction. Here's what we've done. Remember that bead on the wire that I showed you earlier in this lecture? Where we actually showed you a bead moving along a horizontal x-axis? That was the physical motion that we were actually literally watching. We are now representing that more abstractly by a graph with a vertical axis and a horizontal axis. The horizontal axis is time measured in seconds. You can see it down there, 0, 1, 2, 3, 4. The vertical axis is the x-coordinate, or x position of the bead in meters. It still happens to start at 1.5 and go up by 0.5 meter increments to 2, 2.5, etc. And the blue curve that you see is the plot of position of the bead as a function of time. Okay? And we need to be able to look at this kind of abstract position time graph and visualize the motion. And if you look at that blue curve, it tells you that when time was 0, x was 2 meters. If you remember that video I showed you of the bead, that is where it was. It was at x equals 2 meters when t equals 0 seconds. And as the time goes on, the x gets larger. You can see then, follow the blue curve, that the x-coordinate rises to about 4.25 meters maximum. And then as time goes on, the x-coordinate starts to go back, right? And go back and goes through the origin and keeps on going to the left. That's what this curve is telling you. Okay? Okay, now there's other information on this graph besides just the blue curve, the position versus time. It also demonstrates a graphical representation of average velocity for a time interval. Now, right now, the time interval is set at delta t equals 2.5 seconds. The time interval starts at t equals 0 and ends at t equals 2.5. And the delta t is represented by the green rectangle down along the time axis. That's the time interval, delta t. Now, for that time interval, there's a delta x. There's a displacement, a change in position. The initial x is 2 meters, and at the end of this time interval, it looks like the final x is about 3.25 meters. And so the delta x is represented by the red rectangle on the x-axis. See it over there on the left? And then I also have a black straight line that connects 2 dots on the blue curve. At x final, t final, there's a black dot, and then at x initial, t initial, there isn't an actual black dot, but you can imagine one there. And then we've just drawn a straight line in black that connects x, the final point, and the initial point. And the slope of that black straight line in the video, that's V average, because the slope is rise over run. The rise is delta x, the red rectangle. The run is delta t, the green rectangle. Delta x over delta t is, for this graph, rise over run, that's slope. So the slope of that straight line is the average velocity for the time interval delta t. And if you do that calculation here, you'll take 3.25 minus 2 is 1.25 meters for the delta x, divided by 2 seconds for the delta t, and you get 0.5 meters per second. And the animation actually displays that. Now, with this slider, I can change delta t. Okay. Let's reduce the delta t, see how close we can get, to 2 seconds. Now the straight line connects the initial point and the point on the curve when t equals 2 seconds, which corresponds to x equals 4 meters. Now you take the slope of that black line to get the average velocity for that time interval, and you discover it's 1 meter per second. I can make the time interval smaller and smaller. There we are at delta t equals 1 second. And the slope of the black line is now 2 meters per second. And that's the average velocity for the time interval that starts at t equals 0 and ends at t equals 1 second. And I'm now going to take the limit as the delta t gets smaller and smaller with the t initial always being equal to t equals 0. That is graphically the same thing as in calculus taking the limit as delta t goes to 0. Now this slider doesn't let me have delta t go all the way to 0. The smallest I can get is delta t is 0.05 seconds, but it's showing you that I'm approaching a black line here that just glancingly touches the curve. And such a line that glancingly touches the curve at one point is called a tangent line for the curve. So what we see is happening is that as delta t goes to 0, I'm getting a straight line that's tangent to the curve at time 0, and the slope of that line is the average velocity, and the limit is delta t goes to 0, but that's what instantaneous velocity is. Okay? So we're getting to a nice geometrical interpretation of instantaneous velocity. If you have a plot of position versus time, x versus t, the slope of the tangent line to the curve at any given time is the instantaneous velocity of our particle at that time. So what we want to be able to do is take a plot of position versus time, like you see here, and kind of tell the story of how the particle is moving. So now let me show you the same curve. It's really the same position versus time curve. But now the little slider that I have is labeled T1. And as I move that slider, it draws the tangent line in black to the position time curve and gives me the slope of that tangent line, and that's the instantaneous velocity v. So for example, in this position versus time curve, I have the T1 slider set to 0, so the tangent line is at time 0, and you can see the black line there, and you can see it has a positive slope. And it turns out the slope of that line is exactly 3 meters per second. So the instantaneous velocity of the particle at time 0 is 3 meters per second. That means the particle is moving at a rate of 3 meters per second in the positive x direction at time 0. So again, you need to be able to tell me the story of the particle's motion. Let's change the time slider to T1. And the tangent line adjusts to always stay tangent to the curve. We're coming up on time 1 second. That's pretty close. There we are. So now we're at the time of 1 second. There's the tangent line, the black line. The animation tells me that v is 1 meter per second, so that's the slope of that curve, 1 meter per second. That tells me that it's moving at a rate of 1 meter per second, so not as fast, but still moving in the plus x direction. Okay? Can you see from this graph when the particle is at rest? For just one instant, there it is at rest. You see how you find out what it would be? It would be the time when the tangent line is perfectly horizontal. It may be hard to get it exactly. Oh, there we got it. It looks like the time is 1.5 seconds. Then the black line, the tangent line, is perfectly horizontal, which means it has a slope equal to 0, which means the instantaneous velocity of the particle at this one instant is 0. It is at rest for this one instant. Now let's have the time progress. Now we're going up to 2 seconds. Now notice the tangent line has a negative slope. And in fact, the animation tells me v equals negative 1 meter per second. That means it's moving at an instantaneous speed of 1 meter per second, but in the negative x direction. Now moving to the left. Suppose I move up to a time of about 3 seconds. Now it's very steep and negative slope. And I see the velocity is negative 3 meters per second. Okay? There's a lot of information in a velocity time plot, and we need to be able to interpret it. Okay? Here's another question. Which way is this particle, remember it was a bead on a wire, which way is it moving when it passes through the origin? We need to be able to answer that from this graph. Well, you've got to find the velocity when x equals 0. Let's see if we can get it. There we are, that's pretty close, right? The x is 0 here, because the x is the vertical axis. But the velocity tells me, well, how what the rate of change of position is. So I have a pretty large negative slope to my tangent line. In fact, the v is negative 4.12 meters per second. Negative sign tells me that it's moving in the negative x direction. Okay, this is our first introduction to a number of kinematic quantities. I'm going to leave you today by going back to my slide, and I want to refer now to the position time graph that you see in front of you. Okay, right here. Position x and time t in seconds. And you can see a curve there that is telling us the story of some particle that was moving along an x-axis and was observed with time. I'm going to now ask you a series of simple little short answer questions, and I'm going to want you to record your answers, write them down on a piece of paper, and you can pause this video and replay my questions as much as you want, but write down your answers. And then I want you to go to our Blackboard site, and I will have a discussion forum for this video lecture, 2.1. And I want you to go into that discussion board and type your answers to these questions. And this will be considered class engagement. Okay? All right, so we're using this graph of position time that you see encircled here. Here's the first question. When, at what time value or values is this particle at rest? You can only answer based on the curve that you see here. At what time or times is this particle at rest? That's question 1. Question 2. In what direction is the particle traveling at the time t equals 0? In what direction is the particle traveling at time t equals 0? Question 3. How many distinct times does the particle pass through the origin? How many distinct times does the particle pass through the origin? And question 4. In what direction is the particle traveling at t equals 3 seconds? In what direction is the particle traveling at t equals 3 seconds? So, answer those questions in the discussion board that I will post on Blackboard. Okay, that is all for our first lecture.